All right, good afternoon, everybody. Mic on, sounds good. All right, today I'm going to be presenting redfish, bluefish. We're going to talk about improved phishing detection with perceptual hashing. And we'll talk about what that means and some interesting approaches and talk about phishing in general. So I'm principal research scientist for Barracuda Networks, the Barracuda Labs division. We are pretty much the greenfield research arm. We do a lot of stuff kind of in the community, putting out resources, and then our role inside of Barracuda is more generating information sources and kind of doing prototyping, proof of concept stuff that honestly hardly ever makes it into the final products, but occasionally we get a really good find and it does. So it's a great place. I enjoy doing all that. Some of the community resources, and we'll talk about a few that relate to this, are Threat Glass. We did a LinkedIn privacy protector, or profile protector a while back that's been languishing a bit and needs to be revisited, but anyway, a few things like that. Past lives, I've done a lot of offensive stuff, focused mostly on reverse engineering and arbitrary code execution through whatever means. I was at SecureWorks long before Dell, way back in the day, and did a little while doing control system, SCADA security for a while, visiting lovely places like Lubbock, Texas, and climbing around in coal plants. So anyway, why are we talking about phishing? Isn't phishing kind of a solved problem? A little bit passe. I even said that in the abstract I submitted. It's not sexy. Like phishing, it's phishing. But the truth is, it's a problem, and it continues to be a problem. Does anybody follow the Guru on Twitter? He's a great guy. He makes fun of the whole InfoSec world quite a bit and has some good insights, even if he's kind of a jerk about it. But this quote really kind of seems true to me, and a lot of what I've seen is that, you know, we all worry about Ebola InfoSec. We worry about arbitrary code execution. We worry about whatever the latest presentation was at Black Hat about how to get that. The truth is that's not really the problem. Most of the time it's bad passwords are what get you compromised. It's not patching, you know, MS 0864 from, you know, almost a decade ago now. It's bad email security, things like that. So that's why I think we need to maybe revisit some of the older, less sexy topics and talk about them from time to time. So to start off on the ground floor, I'm sure we all know what phishing is. It's a very common term. We're going to look at a few definitions and see maybe how they don't really apply to today's reality. So this is from the Anti-Phishing Working Group that I guess is probably as good as we can get from a, you know, very set definition of things. They've been working on it a while. They're kind of a recognized industry group that does things. So phishing is a criminal mechanism employing both social engineering and technical subterfuge to steal consumers' personal identity data and financial account records. So that's good enough, but it's probably a little bit too pointed for what phishing actually is today. Don't you think? Like, does anybody agree with this definition wholeheartedly? That's all it's ever going to be is financial data. Not really. But this is what most people think of when they hear the word phishing. So phishing, I love this graphic. It was stolen from a great guy, C. Mike Draw. It's hilarious. Love it. So it's often email. But we'll raise it to messaging in general. But most of the time you think of like the Nigeria, you know, 419 scams of some prince trying to get $1 million out of the country, and he just needs you to wire him $100 so that he can wire the $1 million to you, and you can give him, you know, $800,000 when you get back, and everybody's good. Or some high-ranking government official needs someone bribed, but they don't want a money trail, so they'll give you $100,000 if you'll send this guy $80,000. These are terrible, of course. There's some interesting stuff in that, though, that they're intentionally terrible. And it's not something you think about much, but think about how easy it is to send out these phishing emails. You get a botnet to do it. Literally, even if you're paying for it to have done, which some do, some don't, but even if you're paying for it, you're talking about thousandth to 10,000ths of a cent per email sent. So basically no cost at all. But if your victim happens to respond, you have real costs coming in of responding to those phishing attacks to try to get them to actually send the money, right? So there's a certain art and evolution in phishing that happened to make it as bad as possible that you only want your real qualified leads to be coming through and sending you that email, because it costs you money to respond. So in general, when you get a phishing email, if you're smart enough to realize it is, talk to them, waste their time, and let's drop that level down a little bit lower. But anyway, I'll digress. But that's fun. There's a great research paper from Microsoft that I'll include links in at some point. So spam versus phishing. I hate the way we conflate definitions in our industry, because spam has become like this catch-all for everything related to email, to the point that spam doesn't mean spam anymore. So let's scrap that. Spam means unsolicited commercial email, period. Whether it's trying to sell Cialis or knockoff Nikes, that's what spam is. The larger category doesn't really have a name. I like to call it just malicious messaging. It has to do with trying to get you or your computer to do something that you might not want it to, but the attacker does. And phishing is a way that that happens through influencing human factors. I know that seems a little bit academic and all that, but basically, malicious messaging and phishing is just a way to make things happen, using human influence, appealing to our desires, whether it's greed or gullibility. A little bit more about why we're talking about phishing. These stats, at least the top one there, is from the anti-phishing working group again. These are the most recently available stats. So Q2 2004, which ended, June, when quarters end. So there were about 130,000 observed phishing sites during that quarter. And this is from the partners in the anti-phishing working group, because there's quite a few, and they span pretty much everywhere in web security. So that's probably a pretty reasonable number. See a lot of spear phishing attacks in the news. And they tend to be a lot of money, but they're very focused. You know, £1 million here, $1 million there. Not a huge deal for the whole information security industry, right? But they add up over time, and sometimes these are really big deals. You also see a lot of growth in India. So there's some odd reasons why that might be happening, but Indian firms are continuously targeted. I have some speculation that it has to do a lot with kind of the less savvy users coming online. There's 1 billion people, so that makes sense to target it. There's also some level of, cultural deference to authority within a lot of Indian culture that just kind of is part of the cultural makeup there of how you operate, so that, is good for phishers. And there's certainly growing wealth there as technology comes more and more online. There's probably similar numbers in China too, if I had to take a guess, but those numbers really aren't available. But I would guess they're experiencing a lot of the same things. We also see that in this pie graph here, that financial services and payment systems are certainly the most targeted, probably making up somewhere around 55 to 60% of the total market, but by no means the whole market. That's why the definition at the start doesn't really make much sense anymore. There's a lot of other things. There's everything from trying to steal World of Warcraft credentials to PayPal credentials. There's a lot of everything. Not to mention just getting you to install something on your computer that you might not want to. So we in the InfoSec industry are working on these problems, right? There's a lot of money out there. There's a lot of problems to be solved. So we're getting better at this, right? Well, not really. Can anybody out there think of a real advancement in phishing protection since 2006? There's really been none. You got everything from, really, really terrible, like signature-based AV, more or less systems that apply to email. They're usually built on anti-spam detection. Anti-spam is great because anti-spam is, huge, shotgun blast kind of stuff. It works pretty well for that. Statistical filtering. For phishing, if it's targeted at all or if it's done well to look like certain other ones, much harder to detect. Sender blacklist and reputation stuff is about as high as the technology goes. And that is largely unchanged since CipherTrust first released their systems, say 2004, and so basically 10 years and about a dozen acquisitions later, we're still using very similar technology kind of across the board. User education doesn't really seem to make a whole lot of difference. And IP reputation stuff is very similar. On the email side, there are some advancements that work, mostly in the ones that are still related to anti-spam. You got SPF records, you got DKIM, you got APR. Anybody heard of APR? I don't think it's used a whole lot. It's like anti-phishing email reply project. I think it's more researchy, but it's used a little bit. Essentially, the reply emails on phishing stuff don't change very much, where the sender does, because you want to be able to get the reply messages. So there was kind of a basically blacklisty approach to the community coming together and building those lists of bad reply addresses. Kind of there. I don't know if it really makes all that much difference these days, because it's so easy to set up a new, fake Gmail, or not even fake. I mean, it's a legitimate Gmail, Yahoo Mail, whatever address. If you use it once and it goes away after that, you don't really care. What's also interesting, though, is phishing hasn't exactly kept up with the cost of cybercrime generally. So these are estimates, and as always, take estimates a little bit with a grain of salt, because everybody wants to seem like it's more than it is, so they get more money for their budgets, or the vendors can sell more, stuff like that. But anyway, take it with a grain of salt. But $400 million cost of cybercrime globally, whereas phishing only accounts for $6 billion of that. So you're not really looking at much, a very small piece of the pie. But at the same time, that pie has gotten a whole lot bigger. But at the same time, there's not much focus on it at all. It's interesting. You also have the problem of diminishing returns on this, because at some point, it costs a whole lot to protect that 0.001% of users who are greedy enough, gullible enough, whatever, to fall for it versus the rest. And at some point, you really have to hit that kind of inflection point where it makes more sense to just have that as an acceptable cost of doing business. That this is going to cost us X million dollars a year to do business, and it would cost us 3X to solve it. So we're just going to deal with it. Are we to that point? I don't know. I think a lot of people might think we are. Really? All right, apparently that died. Modern advice we see, and I just grabbed a lot of quotes from some recent articles here about it, don't seem that modern at all. Like, I think these things would have fit in very well in, InfoSec kind of trade journal in 2003. Very little changes. You're talking about IDS. Does anybody use IDS anymore? Like, everybody's been kind of past that or on to something else for a long time. But the advice still features it. Everything kind of talks about the perimeter, and everything talks about getting hit by it once, and then we're going to block it past that. Spear phishing, that doesn't work at all. Like, if you're worried about, if you're focused on seeing something a lot of times before you block it, not going to happen. Modern reality is that perimeter defenses are having a very hard time keeping up. We all know that. And I'm not going to say bring your own device, but bring your own device. Changes everything completely, and the perimeter stuff no longer works. People have been preaching that for a long time. We also have the real problem of attackers, these days are more sophisticated because they need to be, but also because the things that they're going after are a lot more valuable, so they can be. So pivoting is not only a very important technique, but it's a very real defensive need. Things that happen to Jim's computer in HR can be a real danger to Jill in accounting. And once you get a foothold inside of a network, whether it's a laptop, whether it's a desktop, a server, what have you, footholds matter. And you can do a lot past that and do a lot to stay in once you're there. So some defensive shortcomings in this area. A lot of it relies on domain names. Domain names are reaching the point of uselessness from a trust level. Not that they've ever been much better than uselessness from a trust level, but it's what we have to build on. It's what we have. The weekly churn rate is, well, you see 810,000. This is from domain registrars. New domains coming online every day being registered. And about 750 go away. Or sorry, this is weekly. So you got 600,000 or 60,000 diff every week of new ones, and that many going away that you have to deal with. So that's hard. Like, are you going to develop a system that works on that? Not so much. You also have this land rush of new TLDs that are just insane. I don't know who's buying these and who's spending the money to set them up, but it's happening, and there's a lot of them being registered. So we get to deal with those problems down the line as soon as consumers start thinking in terms of .whatever instead of .com. And there's certainly a lot of people banking on that happening. Just last week, you had .beer come online, which I'm guessing will be very popular in the Denver area, since you guys are birthing breweries like it's your job. The whole certificates system, SSL, it's just a fiasco and always has been. And every day we see more and more flaws in it. You see the certificate authorities getting hacked. You see Mozilla and Firefox, or Mozilla and Chrome and others having to revoke their trust in certificate authorities. It's just a mess. So you have solutions like certificate pinning that work around making sure that this SSL certificate is only valid for these ones, and these are the only ones we trust. And that's great, right? But that only works for really big sites. For the most part, your local bank, your healthcare insurance provider, if it's at a local level, aren't going to have this. So you essentially have no protection there. And well-designed phishing attacks are going to be using the more local, more targeted stuff, rather than sending out, a billion emails about Wells Fargo. It's going to be, First Bank and Trust out on the corner. So, not a whole lot. You also have a lot of trouble with malicious messaging, not just happening over email anymore, it's social networks. So user-generated content with regards to malicious messaging kind of changes everything. Because not that you could ever validate the sender before, but you certainly can't do it now. And keeping up with the modern social graph is not easy. I've tried. Like developing systems to do it, to keep up with Twitter or Facebook and every new user coming online, it's incredibly difficult. Like essentially you can't do it. You might can spot some malicious users here and there and do some interesting things, but keeping up with the whole social graph and having some notion of trust within that, it's just not going to happen. Except maybe at the individual user level with users you directly interact with. But doing it organizationally, very tough. At the same time, it's trivial to make new malicious accounts on these services. You can see my presentation from AppSec last year in New York about how to do that in some really fun ways. So, getting into more direct fun. So why is phishing so tough to defend against? Basically because it's built around human factors. The important bits that make phishing successful are gullibility, greed, carelessness, and just being generally uninformed. At some point you can blame the victim, and we're honestly probably at that point. But that doesn't mean that you have to do any less cleanup when it happens. So I think we need to look at some new approaches, and maybe some more interesting approaches, and look at how computers look at designing software to perceive things the same way that we do, to better design systems to defend against human factor attacks, which are largely what phishing is. So there's a technique called perceptive hashing or perceptual hashing, and there's a huge range of these. Usually they're applied to things like determining if media is the same, if images are the same. We're going to talk a lot about how that works. They're used in fingerprinting, DRM, all sorts of stuff. Essentially, very broad level, it transforms an image to a hash, which is a fingerprint. It reduces the variance by just getting the important bits. And it gives a concept of distance between images. So this is the same way that essentially lossy compression works. When a JPEG is being created, when you're compressing a full audio file of WAV file or FLAC file or whatever down to an MP3, it gets the important bits and keeps those. This is a much more low level than that, but essentially the same concepts are involved. So there's a couple of different ones. We're going to talk about kind of the algorithms to do it and then see what happens with them. And then talk about how that can be applied to phishing. So there's a few different ones we're going to talk about. Average hash, perceptual hash, which is one of the original ones, and difference hash. So average hash, what we're going to do, you take an image and you shrink it down to 8 by 8. Whatever size it was, it doesn't matter if that doesn't fit, shrinks it down. You convert to grayscale, and then you average the colors and you compute the bits. So you go through each pixel in that 8 by 8 that are left, and you say, is this pixel above or below average for the thing? And average, we're talking about color intensity. So we get down to grayscale, and red, green, blue is gone. So we basically just have a single number that represents the intensity between black or white for a pixel, right? So we just go through and say, Is this above or below the average? And then we build this bit string, or bit, if you want to push it into an integer, same deal, conceptually, and then it makes a hash. So that's the fingerprint of the image, as represented by that. Doesn't matter if the image has been resized, it doesn't matter if the colors have changed because we're converting to grayscale. So what it does is allows you to really do computation and comparison on the structure of the image. I know this seems a little weird, we're going to show you some examples soon. So this is super simple. If you can read in code, it makes it a little bit easier to understand. So this is just in Ruby, which is close to natural language. Basically, we grab all the pixels from a resized image, quantize it means reduce the colors down to rows by, so 64 in this case. And then we export the pixels, we get the average size of it, and then we just compare it to average. I know the code's a little terse, I was trying to save lines because I know a slide full of code is terrible to read for everyone. So, anyway, this is what it does. So the first step is the resizing as it goes there to the right. It brings it down to 8 by 8. From there it reduces the color again, and then just looks at the average to go with it. This is the average hash. The other ones will be very similar, but this is what happens. So you transform an image into a single integer that we can then compare to other images. And if images are the same, they're very similar in their hash value, which lets us know that people are perceiving them the same way. Another hash, this is perceptual hash. This is the discrete cosine transform. I'm going to get into even less detail about this because honestly, if you haven't had like 2 years of pretty heavy undergraduate math, you're not getting it. At least I'm not, and I had several years of pretty heavy undergraduate math. But basically, by decompressing it, you get an image like this one in the side, and that's like coefficients. We won't get into details. But it gets the important values, and it pushes them up towards that top left, and then you can just grab the top left. So imagine if you're taking the discrete cosine transform hash of an image with someone in the foreground, that would kind of move up to the top left, where everything in the background would move down to the less important bits in the bottom right. And then you can just throw those away because they're the least important bits of an image. So very cool, and you wouldn't think it would work when you look at it, but it does. It's very cool. One of the more fun ones, and ridiculously fast to compute because you don't even have to do the average, is the difference hash. We're going to be using this in most of our examples along with average hash. So here you reduce the size, reduce the colors, and then you just compare each pixel to its neighbor of if it's more intense or less intense. So you don't even worry about the average. You just look to your left and say, am I brighter than that one? Set my bit. If I'm not, set it to 0. So, cool. Everybody have a basic understanding of how hashing works? I think got there a little bit. That's the Ruby code for it, and that's mostly for being the slides for future reference, and all the code's going to be published to GitHub anyway. So how do you tell the difference between images? So these hashes, once they're done, revolve on the distance revolves around the concept of Hamming distance. Anyone familiar with the term Hamming distance or perhaps signal distance? So it's a term used in telecommunication a lot of how many transforms would have to happen to a string of bits to convert it into another string of bits. So you see at the bottom, this is the best way to illustrate it. The first line of bits and the second line of bits are identical except for the 3 bits that are highlighted, right? So that would have a Hamming distance of 3 because you have to change 3 bits from the top one to get to the bottom one or the bottom one to get to the top, right? So in this case, between 2 images, if the Hamming distance is, say, 3 or less, and this depends on your image, your criteria a little bit, but that's almost certainly a match. If it's between 4 and 10, for the most part, it's going to be still a likely match, but possibly a false positive. And if it's greater than 10, basically they're not the same image. Or they're too different to be able to say they're the same image. And we'll see some examples of that in a second. It's essentially an error rate message, or measurement. So we have a project I mentioned before, Threat Glass, that we've been playing with a little while. We launched it earlier this year, I think around RSA. And it's built around documenting and showing how users perceive and are affected by malicious sites, like what they see, what their browser does, and how the user does it. So the way we do it is we have a system that goes out and visits basically any URL we send it to. We have it hit the Alexa top 100,000 every day, and then we have other ones that go in a one-off thing multiple times a day. And what it does, it visits the website, it takes screenshots as it visits the website. We're also collecting the packet captures that happen at the time, grabbing artifacts, and doing lots of other fun stuff. So it's got a big corpus of PCAPs. This is completely community resource, no sign up to use it, no nothing. Use it, it's great, it's fun. Love for more people to use it. But anyway, we get to some interesting stuff. So this is a drill down into one particular site that was compromised for quite a few days. This is what an individual page of Threat Glass looks like. This is trsanet.info. No idea what it does, doesn't matter. It happens to be right at the top 10,000 or so most popular sites on the web. So that's a non-trivial number of people visiting it every day. The Alexa rankings, with the caveat they're a little bit flawed because they bias towards non-technical users because of how the stats are collected with an installed browser toolbar. But for this case, that makes a lot of sense because you want to be talking about how this affects the less savvy, untechnical users. Those are the ones most likely to be infected or dealt with. So we have several different times that this is infected. We want to see, are they infected by different things? Did the user experience different stuff? Or was it just the same? Was it just a website compromising their system? So we can look at the hash of the last screenshot of what they saw. This is the user's last image as they visited the site. We can tell, as an individual, I can tell that went to the same site. It installed some malware and it redirected to Adult Friend Finder. Not a big deal, right? But for a computer to be able to tell that, that's pretty difficult because it's got, the big thing there. You take screenshots, they're going to have different times, so they're clearly going to have different, file sizes, different MD5 sums, that sort of thing. But with perceptual hashing, we can apply it to those two images and look at the distance between them. In this case, we have 7 for the difference hash and 0 for the average hash. So this allows us to computationally say, these are basically the same image. That's kind of interesting, even though they're not the same image because you got the big pop-up, but with these algorithms, you can tell it's pretty darn close and it's probably a match. You can also look at rendering websites easily. This is a little bit of fun code on how to do this. Because, of course, you don't want to open up a browser, go to your website, take a screenshot, and compare it yourself against a corpus. No, you develop your big database of interesting images to compare your finds against. One good way to do it is use Capybara. I like writing a lot of Ruby because it's easy to write, and it kind of works with the way I think. Capybara is a headless testing suite designed for use around testing usability of websites, but it also lets you visit websites, take screenshots, it runs the full JavaScript, and lets it interact. And these days, really, you have to run the JavaScript to see what a page actually looks like to an end user, right? Because that's the world we live in. So it lets you do some interesting things. And it lets, grab the full screenshot of the page. This also lets you know if someone's basically copying your whole design, if you care about that from a, PR, marketing kind of thing, if you care about protecting your brand. So we had an interesting story and kind of a terrible find with the whole ALS Ice Bucket Challenge. We found a lot of spam revolving around trying to sell people stuff, but also some legitimate malicious messaging. You're sending binaries, malicious binaries, along with an ALS thank you message with receipt.doc, trying to encourage people to open it, right? So this is the kind of phishing that's pretty difficult to detect, right? Because it looks, this is the bad one in the bottom left corner, and that's the actual good one from the donation I did this morning to compare it. Side note, it was very difficult to find anyone who had actually donated to send me an email with the thank you, so I did it myself. I don't know, odd. But anyway, very similar, but clearly it wouldn't be hit by statistical stuff. Like your traditional spam filtering wouldn't be there for comparing these two emails to see if they were the same, or to see if they were even doing similar things at all. You'd be relying on a lot of older stuff. You'd be relying on if the binary is malicious, if you've seen it before, that sort of thing. Which is good, but if you've never seen the binary before and don't have any previous experience with it, that can lead to some trouble. So we got the good one in the top right, bad one in the bottom left. using this perceptual hashing, they're clearly completely different as well. So we don't have anything good there, right? But with this, you can do image extraction. So you can go through an email and see all the images that are in it, right? And we can take fingerprints of those images. You can then associate it with, say, a good known sender list pretty easily. Like no one except for ALS.org should be sending stuff with these images, right? So you have a fingerprint of the image. If that fingerprint shows up in associated image with any email being sent, especially like, the gal's signature, her face, that's a tip-off. That's a useful, flag to set in your phishing detection system. And this isn't like, cure-all or anything, but it's interesting, help out a little bit, give you more stuff to build on. So what you'd want to do, kind of a generalized thing, is you develop a corpus of known good sites or email templates, things that are, what PayPal looks like, what eBay looks like, what your, healthcare that your organization uses website looks like, that sort of stuff. And then you can filter as stuff goes out. And if you're hitting a site that looks a lot like your site, but like a known good site, but it's not that known good site, that should set up alarms everywhere. Okay, calculating the hashes of big stuff gets a little bit fun in the optimization world. We'll talk about that some as well. But it's pretty simple, and it's stuff that scales fairly well. And it's easy to set up kind of the trusted sender list. So the optimizations that you can do, and the caveat, don't use any code that I put up here in production, like period. Not tested, it's to show the idea. It's not, not protected, doesn't do anything right. But anyway, it's Ruby because it's fun to write and it looks good to read so you can understand. JRuby might be promising if someone wanted to port it to that. So the interesting thing about looking at this is it works until you have a huge corpus of fingerprints to compare against. And then you're having to run that constantly. But Postgres has got some really interesting things to build on. And unfortunately, it's kind of a case-by-case basis, but I can point you in the right direction. It's got this generalized indexing sort of thing with gist, so you can build index around Hamming distance between images. So you can quickly search a corpus and say, give me everything that's close to this to do your candidate matches back and forth. This should also probably be very tailored, as I mentioned before, because this is going to work best at the targeted kind of user level, maybe executive, who you want to protect, maybe general in the military, or somebody with some sort of knowledge or access that you would want to protect. But it also works well at the organization level for compared to your healthcare, compared to internal systems that you're not going to have much protection around in other ways because they change all the time. But you could easily have a system that goes through internal systems. I'm saying system a lot. You could easily have a system that goes through your internal websites, intranet stuff, and screenshots that or fingerprints it along with screenshotting it, and then you can easily see if something's masquerading as it. You set up your various protections around it, whether the perimeter, whether you're having your users go through a VPN to access stuff. You have a lot of choke points for interesting bits. It also opens the way to a pretty easy browser add-on that I wanted to play with but didn't have time to implement. So some good references and inspirations that are in the slide deck for link to give some great credit where credit's due. Hacker Factor blog. It's a guy who's been doing some really interesting image forensic stuff for quite a while, going as far back as like Black Hat 2003, 2004. Like he has some really interesting stuff on these, and his is more about detecting the same pornographic images that have already been blocked from uploading, but the same techniques apply kind of across the board. 10i, any of you guys ever used this? It was popular for a little while. It's kind of fallen off, but it's basically a reverse image search. It uses very similar algorithms, but of course it has a very small corpus because if they're trying to index everything on the web, it doesn't work. Phash is a open source with commercially available options to do this. And phashing is a great Ruby gem that does it. I implemented it kind of myself because phashing uses C libraries, C bindings that aren't cross-compatible across all the different things. But anyway, fun stuff. So There's the contact info at the end. That kind of concludes our presentation. That is a very nice barracuda that I caught a couple weeks ago. It was around 18 pounds. Happy days. Code will be available and slides posted. But anyway, that kind of concludes our time. We got about 9 minutes for questions if anybody has any. Otherwise, I hope you found it interesting, and thank you. Right. So if it's this, well, I mean, if the domain name's the same, then you've already compromised the site, right? No, no. Like, so that would depend on where you're. The question is, to repeat it for, I guess, YouTube and everybody else who's streaming it. If the site HTML is the same and domain is the same, is that correct? Okay, so then you could correlate those two. So you can't just look at them individually and say this image and this image are the same or different, because you need context around it. So the context would be like the domain name, other artifacts that are requested off the site, things like that. And that lets you see this is how the person saw it, or how the person is currently seeing it, and it's identical to this known trusted site we have. So that sets one flag. It's also a different domain, so that would immediately set another flag, that sort of thing. And it lets you have more confidence in what you would block. It's only a small part of what would go into the whole thing. That's why it's just improved phishing detection, not surefire, doesn't work for everything, but gives you another very good data point that can be, with today's computers, calculated pretty effectively on the fly. So we don't need to know what domain you're using. We just need to know that it's not the same domain that we have as a known trusted one. Yeah, we just know you're trying to look like one that we're saying is trusted. And that's bad enough. You're trying to look like a trusted one and you're not the trusted one. That's enough to set off, higher warning flags than just visiting a site. Because if you have, your dumb network filtering appliance that's just looking at domain names, it's got to have that blacklist that you mentioned already populated. This, it doesn't. It just needs to have, some known good sites that your users visit often and put in credentials, whether that's PayPal or eBay, or whether it's internal internet stuff, or, some hosted platform you have out there, Salesforce, what have you. If you can detect your users trying to go to a site that looks exactly like Salesforce, but is not Salesforce, then that's a reason to block it. And then either whitelist or blacklist on your networking device, filter whatever happens after that. Does that make sense? Back. Honestly, I can't think of any off the top of my head, because resizing works. Honestly, the ones that are the cases where it doesn't work directly as described are if they've changed the layout slightly but are using a lot of the same elements as a web page. So say the normal web page would have the login in the center and the logo on the bottom right, or vice versa. And the phishing website has all the same elements, but they're in different positions on the page. If they are important enough elements as defined by the way the hash works, if it perceives those parts as being the most important, but they've changed location significantly, then it wouldn't work, because they're not the same image. So those, I guess it's not exactly surprising if you understand how the algorithm works, but you can get around that by doing similar things like I described with pulling the individual parts out of the image. So then you're not looking at the whole of it, you're looking at portions of the page. So you can take screenshots here and there and then just compare it to every other screenshot it took of the page. So you cut a website into 8x8 or 6 by 6, something like that, and then you compare it across the board to the others. You can also do, this is off the cuff completely, but some interesting stuff with, like when you look at Chrome developer tools or Firefox, when you select an element in the element or the Navigator Explorer, it knows like what portions of the site that correlates to, right? So you can hook into that as well and just render those portions and compare that against known good ones as well. And then even if they change the name, change the identifier, if it looks the same as a lot of stuff from the other one, from the known good one, then you could flag it as well. Great, thank you. Anything else? All right, thank you very much, appreciate it.